Welcome to my presentation. My presentation title is Estimation of the Source Fault Model for the February 13th, the 2021 Fukushima Oki earthquake using surface displacement data from PS in SAR analysis. This is today's contents. The Fukushima Oki earthquake of 2021 was a magnitude 7.3 earthquake that struck off the coast of Fukushima Prefecture on February 13, 2021. This area is where the Great East Japan earthquake of 2011 occurred in the past. As you can see from the seismic map, this area has a high frequency of earthquakes. This earthquake is said to be an aftershock of the Great East Japan earthquake of 2011. The Geospatial Information Authority of Japan, GSI, estimated the source fault model of the earthquake by using the results of the surface displacement measured by the Global Navigation Satellite System during the earthquake. As a result, 4 features were revealed. First, reverse fault motion is estimated on the fault plane that tilts southeast with a northeast-southwest strike. Second, the estimated horizontal position of the fault plane is consistent with the epicenter distribution. Third, the upper end of the fault is located at a depth of about 38 kilometers. Fourth, the estimated moment magnitude is 7.1. However, there is still one issue with this estimation result. The issue was that the source fault model was not uniquely determined. This is a diagram of the posterior probability distribution of model parameters obtained during the estimation. As you can see in the figure, some parameters are not uniquely determined. The main problem with this estimation is the use of GNSS data, which is spatially sparse. Therefore, the main objective of this study is to estimate the surface displacement using INSAR analysis as input data to estimate the source fault model. Results are compared with GNSS data to confirm the validity of the results. In this case, we used the PS in SAR analysis to perform the INSAR analysis. The main flow of the PS INSAR analysis is shown here. The removal of the atmospheric component was achieved by using a moving average process. To estimate the amount of variation in the vertical and horizontal directions, we used a 2.5-dimensional analysis, which allows us to project the obtained displacement in the vertical and horizontal directions along the vector plane defined by the 2 radar irradiation directions. I used the equation on the right. Here is the dataset used and the analysis conditions. We used 65 scenes for each of the 2 orbits, descending and ascending. We also used 65 scenes for each of the 2 orbits. We used the gamma application for the analysis. The multi-look was set to 1 by 1. And the amplitude dispersion index used to select the PSC points was 0.15 and 0.25. Here are the analysis results. The PS points with high coherence are obtained on the plains, not in the mountains. This indicates that the PS in SAR analysis results are well done. Both figures show the surface displacement before and after the earthquake, from February 9th to February 22nd, 2021. The left figure shows the surface displacement in the east-west direction, and the right figure shows the surface displacement in the vertical direction. In both figures, the surface displacement is within plus or minus 15 millimeters. This is in good agreement with the order of variation obtained by GNSS. Comparing the results of GNSS with those of the east-west direction, the westward surface displacement in the coastal area and the eastward surface displacement in the inland area are obtained in both figures. Therefore, it can be said that the results are in good agreement with GNSS. The results of these analyses are suitable as input data for the estimation of the earthquake source fault model. And this is summary. Thank you for watching until the end.